Hi, I'm John Garrock. I am a graphics driver performance lead here at Intel. I am pleased to be here today with my teammate Alan Hux, and we are going to be talking to you about DX12 sampler feedback. DX12 sampler feedback will enable developers to maximize GPU performance in new ways and unlock new GPU algorithms. Sampler feedback is one of the new features introduced last year as part of DX12 Ultimate. This sampler feedback session will focus on texture space shading. We will also be leveraging learnings that we have picked up from UL's 3D Mark sampler feedback feature test. There are two types of sampler feedback. There's MIP region used and min-MIP feedback. Sampler feedback surfaces are paired surfaces. There's a sampler feedback surface that is paired with a surface that will actually be sampled with real sampled data. You could think of sampler feedback as the inverse of texture sampling. Instead of reading texels and averaging them to produce a color, sampler feedback instead will write results to a feedback to tell us which MIP regions within a surface would be sampled. A byte in a sampler feedback surface will represent or correspond to a MIP region in the paired resource. Intel's Xe GPU now currently supports both modes of DX12 sampler feedback. MIP region used. This sampler feedback method is very useful for texture space shading. It provides us feedback of whether a MIP region is used within a given MIP in a paired sampler feedback resource. A texel value of 0xFF will tell us that MIP region was referenced via a sample operation. The other sampler feedback method is min-MIP feedback. Min-MIP feedback tells us the minimum MIP that needs to be resident for a sample operation to complete. Stay tuned for Alan's talk, for he will fill in all of the details. Texture space shading. Texture space shading is a very simple algorithm. We essentially calculate all lighting of a texture in texture space, rather than calculating the lighting of a pixel during forward rendering or during deferred rendering. To implement texture space shading, we perform all lighting calculations in texture space. Then, in a subsequent pass, we render the scene again and reference the texel shaded data. So why use texture space shading? Well, texture space shading has many advantages. The first primary advantage is reuse. So a couple scenarios. Reuse can be done for a scenario like VR. We can shade once in texture space and then reuse those shaded texels when rasterizing the scene once for the left eye and once for the right eye. Another reuse opportunity is temporal reuse. So an object that is shaded in the scene may not change over frame. So if we can light the object once in texture space and then sample from that texture space shaded texture to rasterize that object correctly until the application determines that lighting needs to be recalculated. Another performance method for texture space shading is the decoupled rasterization from shading rate. So the way that this works is by decoupling the shading rate, we can actually increase performance at the cost of visual quality. This can be done by increasing or decreasing the sampler bias. For example, if we need to increase performance, we can increase our sampler bias such that we sample from a higher level MIP in the MIP chain. When we sample from the higher level MIP in the MIP chain, this will encourage us to shade less texels in texture space and thus increase performance. Another advantage to texture space shading is, and this is referenced from the Microsoft spec, is that it can remove shimmery artifacts from faraway objects. So how does sampler feedback help us? Well, for texture space shading, less texel shaded equals better performance. Sampler feedback will tell us within a certain amount of accuracy which texels will need to be sampled during rasterization. With this information, we only need to shade the texels that will be sampled during rasterization. Typical flow for sampler feedback would be begin the frame, populate your feedback map, engaging the feedback texture 2D write sampler feedback API. Then, after the feedback map is populated, we would resolve the resource into a uint8 format. Then, when it comes time to shade the texels, we check the feedback map, and if the feedback map has a value of 0xFF, we know that we need to shade that texel. Once all texels are completely shaded, we can perform our final rasterization step and reference all of the texels that were shaded. Our partners at UL have developed a 3D Mark sampler feedback feature test. This feature test implements texture space shading using DX12 sampler feedback. Here is an example of what the workload looks like. It looks like a normal rendering of a regular deferred rendering scene, but as we will see in a little bit, everything is actually shaded in texture space and fully rasterized using texture space shaded texels. In the next video, I'll show you the same scene again, this time showing the textures being shaded in real time. The texels that are illuminated are the only texels that are being shaded. Anything that's black is not shaded because sampler feedback enabled us to skip shading those texels. The 3D Mark sampler feature test was designed to benchmark the performance of sampler feedback. It's implemented in two modes. There's the DX12 sampler feedback mode, which engages the DX12 sampler feedback API. The other mode is a software emulated sampler feedback. It was implemented using a very highly optimized compute shader, and the results of this are very good. The net benefit of the workload using sampler feedback is 23% faster than the emulated path. Sampler feedback pass itself is 3.1x faster than the emulated sampler feedback pass. I would classify this workload design as a deferred rendering approach, yet using texture space shading. We will go into further detail in each of these render passes. Before we get into that though, there's 3 steps that need to be done before we can begin rasterizing our scene. First, we need to create a sampler feedback resource. We need a resource that's created with a MIP region used resource format. We need to define a MIP region size. Next, we need to create a paired resource. This paired resource is the resource which we will actually use during texture sampling operations after texture space shading is done. Lastly, we need to create a feedback view. This is a special feedback view that references both the sampler feedback resource and the paired texture. This is done with the create sampler feedback unordered access view API, and this will map to your feedback texture 2D in HLSL. Now we can begin rasterizing our scene. The first step is somewhat of a depth prepass combined with the ability to collect UVs and gradients. What this pass will do will enable the depth test, enable depth write, and will only write out UVs and gradients of that UV to 2 render targets when the depth test passes. Next in the pipeline is the pass where we actually engage the sampler feedback hardware. This pass is implemented as a full screen pixel shader pass. The first step of this pass is to load the UVs and the gradients generated in the previous pass. Next, we simply call the write sampler feedback grad API with the inputs that were loaded, meaning we performed the write sampler feedback grad call with the loaded UVs and gradients and a given sampler state as programmed by the application. One interesting performance tip: applications can stochastically skip calls to write sampler feedback grad. In this particular case, this pass is 25% faster when stochastically skipping samples. If you implement this optimization, please ensure that you have proper image quality. Next in the pipeline is the resolve feedback stage. This is simply done by calling resolve subresource region with the D3D12 resolve mode decode sampler feedback enum. After all of the texels are resolved, the feedback regions that are touched will have a value of 0xFF. Images on the right will help visualize which pixels were touched for a given scene in the 3D Mark sampler feedback feature test. One performance tip for this phase would be a reminder to batch all resource barriers into one API call. We can resolve all sub-resources for a given MIP chain using uint max as the sub-resource index. One interesting optimization that UL added was a compaction pass. The compaction pass will try to avoid generating redundant compute shader threads for the texture space shading pass. So what this does, it will look for MIP regions that don't have any texels touched, and per compute thread, if no texels are touched within a MIP region, then we will not launch a compute shader thread to shade that region. So essentially what we're doing is we are cutting out redundant compute shader threads within the texture space shading pass. So what this pass does is it builds a list of thread groups that are needed to be shaded using texture space shading, and it gives us a thread group count for all MIP regions that need to be shaded for the texture space shading pass. And part of the output of this pass is that we have an XY offset per thread group. Next is texture space shading. We're not going to go into the details of texture space shading, but we are going to reference everything that was done in the pipeline up until this point in time. After the feedback compaction is done, the workload will dispatch the minimal set of threads needed to shade all texels that will be referenced when rasterizing the final scene. Again, this is implemented using execute indirect. One performance tip that I thought was very clever in the application is that when shading a MIP in the MIP chain that was MIP 1 or higher, the developers had a neat optimization where if the parent MIP had all of the 4 parent texels shaded, the current MIP would sample those parent texels and then average those results and then store the results from the parent texels into the current output of the texture space shading pass. This allowed the lower level MIPs to skip the costly lighting phase in texture space shading. And now we're at the end of the pipeline. So the final output is produced using a full screen pixel shader pass. We shade using the paired texture. The pass will simply sample from the paired texture, and it will use all of the same sample input parameters from the sampler feedback pass. This means the pass will be using the same UVs, the same gradients, and the same sampler state as the sampler feedback pass. I'd like to give a special thanks to our partners at UL for developing this workload. Please look for this feature test coming in Q3 of 2021. One topic we didn't cover in much detail was MIP region size. Again, MIP region size will map a texel and the sampler feedback resource to a MIP region and the paired texture resource. One thing I want to highlight is that different resource sizes will change the performance of the workload. The smaller the MIP region, the higher level of granularity a MIP region used would give you. This has some performance artifacts I'd like to discuss. Essentially, a smaller MIP region will mean that the size of the sampler feedback resource will proportionally go up as the MIP region size goes up. This will result in a higher cost of clears and a higher cost of resolves and a higher bandwidth cost. But on the flip side, we have potentially less shaded pixels due to the higher resolution of the MIP region. One could visualize a MIP region like so. On the left-hand side, we show our 1 byte highlighted of a MIP region of data from our sampler feedback resource. You can see the 4x4x1 MIP region has a red pixel that maps to the image on the paired resource on the right. So a 4x4x1 MIP region will be represented with more data overall rather than a 8x8x1 or even more so a 16x16x1. For example, 1 byte in the 16x16x1 feedback resource will represent a MIP region of 16x16x1 on the paired resource. But here's the important part. Here's how the performance had changed with different MIP regions. As we could see, the feedback, clear, compaction, and resolve all had performance swings when going to lower sized MIP regions. On the flip side, the texture space shading pass had a change in performance as well. I recommend that all developers try MIP regions and see what works best for all given hardware. So Intel Gen 11 processors all support sampler feedback. Give it a shot and see what happens. We can't wait to see what everyone develops and how this feature evolves over time. Well, thank you for watching our session on texture space shading using DX12 sampler feedback. Next up is sampler feedback streaming with Microsoft DirectStorage. Alan, please take it from here.
Thanks, John. Hi, I'm Alan Hux. We're at the beginning of a sea change in visual fidelity for PC games. We're going to see cinema quality assets that would have thrashed GPU memory enabled by high-speed storage and new D3D12 APIs. Games will stream just what the player sees, just in time. We have some new tools to help us achieve this vision. D3D12 introduces sampler feedback to identify what to stream, and DirectStorage for Windows provides fast, low-latency file I/O. Let's look at an example of sampler feedback streaming. This scene contains 1,000 planets, each with its own 350 megabyte texture. None of the textures are reused, but I am reusing asset files. That's 350 gigabytes of assets. Without streaming, the GPU would be paging assets every frame, and performance would be terrible. With streaming, this scene is only using about 230 megabytes of physical memory. Only 0.06% of the assets are physically resident on the GPU. The first technology we need is a way to manage memory. For this, we use D3D12 reserved resources, also known as tiled resources. Reserved resources act like virtual alloc in C. When you allocate the resource, it doesn't take any physical memory yet. Then you can physically commit portions of that texture at tile granularity on one or more D3D12 heaps. Reserved resources are 64K in size, and the tile dimensions are a function of the texture format. For BC7 format, the tiles are 256 by 256. Here, we're looking at some geometry with a single 350 meg 16K by 16K BC7 format texture, allocated as a D3D12 reserved resource. Now, along the bottom, I'm showing the MIP layers of the reserved resource. On the left is MIP0, MIP1, MIP2, and so on. Where we see black, tiles haven't been loaded. MIP0, for example, is all black. As I move around, you can see different tiles are being loaded and evicted. If I set the texture color to match the MIP level, you can see how the resident tiles correspond to what's visible. A single 1 gig heap was more than enough memory to hold all the tiles for all 350 gigs of the textures in my sample, as long as the application intelligently loads and evicts exactly what it needs. Objects outside the view, portions of textures that are facing away from the camera, tiles that are too high resolution for the display, those are all discarded. To know which tiles to load or evict, each texture is paired with a sampler feedback resource. The feedback resource records which texels would be read by the sampler, whether they're resident or not. Applications can read the feedback resource to determine which texels they need to stream or evict. John talked about sampler feedback's two modes of operation. The first mode, which returns a full MIP chain, is useful for texture space shading. The other mode, called min-MIP feedback, returns a single layer resource ideal for streaming. As John described, sampler feedback resources have a region size that is no smaller than 4x4. If we set the feedback region size to match the reserved resource tile dimensions, we get a very efficient map of which tiles to load or evict. In the planets demo, each 350 megabyte texture is paired with a 4K feedback map. Each bite-sized texel of a min-MIP feedback resource represents the minimum MIP layer of the texels sampled in that region. For example, if a single texel was sampled by the hardware in the top left of MIP0 in this texture, in orange, the min-MIP feedback would look like the following on the right: 0 in the top left and FF everywhere else to indicate nothing was sampled. From the min-MIP feedback, which tells us what texels we need, we can construct a min-MIP map which describes what portions of the texture are resident in memory. Each texel of a min-MIP map contains a number representing the minimum MIP resident in that region. If we load the texels for that region and corresponding regions of every lower resolution MIP below that region, we won't have any artifacts from anisotropic or trilinear filtering. In this case, of course, the regions correspond to reserved resource tiles. The application then loads tiles corresponding to min-MIP feedback, 3, 2, 1, 0. The result is a min-MIP map, which the application uploads to the GPU to use as a sampler clamp, so the application only samples from resident tiles. Here, in the top right, I'm showing the min-MIP map. For streaming, we load the tiles from bottom up 3210 and evict from the top down 0123. This way, the resonant texture data always forms a min-mip map with no gaps between layers. The demo depends on this. Rendering runs asynchronous from streaming, and so we may not have perfect texture data at render time. But since we have the appropriate lower resolution texture data, worst case, things are a little blurrier than we'd like. Ideally, that's imperceptible. If I overlay the min-mip map colors, the tiles become clearly visible. Notice how, even though adjacent tiles are at different MIP levels, there are no cracks or seams. That's because sampler feedback is telling us exactly what we need, so there are no artifacts. If I set each tile to a random color, lock the frustum to this view, and move the camera, we can see that tile resolution drops with distance from the viewpoint. We can also see that outside the frustum bounds, all the high-resolution tiles have been evicted. This is a huge memory savings. This sample is intentionally aggressive about memory management, evicting tiles in as few as 2 frames. Applications would probably delay evictions for a while, maybe a few seconds. The application is constantly determining what to stream based on sampler feedback and constantly mapping texture data with reserved resources. But how do we load the tiles? First, to simplify streaming, texture files are pre-swizzled in the tiles, so loading the tile requires just one contiguous 64K read. File streaming is complicated and difficult to do efficiently, requiring a lot of careful bookkeeping. The best solution for low latency, high bandwidth file streaming is DirectStorage for Windows. DirectStorage provides a simple interface to load tiles direct from disk. I provided file offsets, destination resource tiles, and a D312 fence to signal when it's done. DirectStorage handles all the bookkeeping for upload buffers, command lists, file events. It makes this kind of tile-level streaming much more accessible. Plus, it's more efficient than previous file I/O APIs, leaving more CPU performance available. In this sample, DirectStorage replaced hundreds of lines of code and a dedicated CPU thread. Intel has been working closely with Microsoft on DirectStorage for Windows to make sure our products are ready the first day it's available. Like our partners at Microsoft, Intel can't wait to see the innovations that we built on top of this API. By combining reserved resources, sampler feedback, and DirectStorage, we get a demo that is constantly adapting to the scene. While the application is running, we can see the heap occupancy change over time, and we can see the bandwidth. For this demo, bandwidth is modest, under 100 megabytes per second for a 1920 by 1080 display. In extreme scenarios, we are limited only by system properties like PCIe bandwidth. With the overlay on, we can see how tiles are streaming to all the planets. The demo limits the amount of GPU time spent processing feedback, so planets are only updated every few frames. Concluding, current Intel Iris Xe graphics processors and future Intel discrete GPUs support sampler feedback, so you can try building applications using it for texture space shading and sampler feedback streaming today. And Intel is ready when DirectStorage is available. DirectStorage will make streaming even easier to implement while improving efficiency. Thanks for watching. To learn more, follow the links provided.